All right, folks, this is part 2 of forces and potential energy functions. And the point of this video is to really get a nice review of equilibrium and see how we can find out equilibrium locations looking at the potential energy graph. All right, so quick review of equilibrium. Definition of equilibrium is that the sum of the forces on the object are 0. Since F equals ma, that means A is 0. A common misconception is to think that that means that the speed is 0, because a lot of things are just chilling in equilibrium. So the acceleration is 0 and the speed is 0. That is not true. Only this is true. So let's do a quick review of the bungee jumper. So remember, the bungee jumper jumped, and as long as mg was bigger than k delta x, they were speeding up because the net force was down and the velocity was down. For one brief instant, k delta x equaled mg, and that actually meant the speed was a maximum, because after they continued to move, then, mg stayed the same, but k delta x kept getting bigger and bigger. And then the upward force was winning. And since the bungee jumper speed was down, but the net force was up, they began to slow down. Okay, so what we're going to see is that objects can pass through equilibrium and their acceleration is 0 just for an instant. And you've seen it before, so hopefully thinking about the bungee jumper again was a good reminder of what was going on there. Okay, so now we're going to tie this back to what we said in the first video. If the force on an object is 0, because it's in equilibrium, and if force is negative du dx, first of all, we don't care about the minus sign because negative 0 is still 0, so we can be a little bit sloppy about the minus sign, but don't be. Then maximums and minimums of potential energy functions are where the force is 0. Because if F is minus du dx, and we want to find out when that is 0, how do you find the max or a min? You take the derivative of a function and you set it equal to 0. So if it's a minimum, then your speed is at a maximum point, just like the bungee jumper. If it's a maximum, then your speed's a minimum. But really easy free points is when you look at a potential energy graph, they'll say identify the points of equilibrium, just the max and mins. Super easy. I know there was one hard derivative on the last homework assignment, but I just pointing to them and identifying the max and points of equilibrium, super easy. Okay, you need to know 3 types of equilibrium because there's a maximum, and there's a minimum. Sorry, that's not, there's max is 1, min is 1, and there's a third type. So the first type is called stable equilibrium, and you do need to know that term. The reason it's called stable is, again, think about the roller coaster. If I take this marble and I move it to the left, then the force is going to pull it down to the right, trying to get it back to equilibrium. It's going to overshoot equilibrium and it's going to end up on the other side, but the force is always trying to bring it back towards equilibrium. So if there is energy loss, it will oscillate and eventually come back and come to rest in that stable position. Okay, that's called a restoring force because the force is trying to restore equilibrium. So a mass on a spring bobs up and down, and again, with friction, the periods should stay the same. With friction, it will eventually end up right there. That means that's your equilibrium position, because that's where it wants to end up. The amplitude gets smaller and smaller and smaller until the amplitude is 0, meaning I have no more energy. Okay, so you can also see that if this is the position versus time graph, the slope is the biggest as it passes through equilibrium. And the slope is 0 at your turnarounds. But the speed is the biggest at equilibrium, which reinforces what we already know. If something is oscillating back and forth, that's where your kinetic energy is a maximum. Maximum. And it's 0 at the turnarounds. Okay, so it's easy to get confused about that stuff, but know when the speed is 0, know when the speed is a maximum. Okay, that's stable equilibrium. Unstable equilibrium is, classic example is, let's say you had like could be a roller coaster or a cone-shaped thing, and you put the marble at the top of the hill. If it moves a little bit away from where it's balanced, right, it would be in equilibrium here, but it's an unstable equilibrium. Because if the wind blows, then the force is this way and the motion is this way, and I'm just going to move away from equilibrium, not back towards it. Or if I get kicked over a little bit this way, the force is going to be this way with the motion, and you're going to move away from equilibrium. So if a particle, for whatever reason, gets pushed away from equilibrium, the force from the potential energy will continue to push them away from equilibrium. So a classic example of that is if you have a cone and the cone is very carefully balanced, but if there's a slight wind, it'll topple over. Also, if you remember the demo I did with the magnets and the carts, I think there was a way to have it be, I think it north and north, north and south. It was happy, but if it moved in either direction, then it was pushed away. I can't remember quite the configuration, but I don't want to waste more time talking about that. Okay, the final equilibrium is if you have a marble on the lab table, the force is 0. And if I move it a little bit to the right, that slope is still 0. And if I move it a little bit to the left, the force is still 0. So that's neutral, that each of these locations have the same stored energy. So it's neutral. If it moves in either direction, the force remains 0, still in equilibrium. Okay. A couple of more relationships, just because I think they show up on the formula sheet, and I don't want you to be confused. Definition of work was F dx. Technically, there's a cosine in there. But if F equals minus du dx, to undo that, then the change in potential energy is the negative integral of F dx. That is really important for those of you taking the AP. If you are going to derive the real potential energy function for gravity, that's the second gravity module. Make sure you do that. Okay. So we're going to talk about this more in the final lecture, deriving our own potential energy functions from nonlinear springs. But what I find a little confusing is I think there's more clean ways to talk about this that make more sense. But sometimes some textbooks will say the change in potential energy is negative the work done. Technically, it's by the force. By the force of gravity, by the force of spring, by the potential energy force, not by the person fighting the force. So again, I find this little just working around what should make sense, but let's just see what we're talking about here. Let's say you have the force of gravity and the object goes from point A to point B. Gravity's doing negative work because the motion is up and the weight is down. So let's just say gravity did, the work done by gravity was minus 60 joules, right? Did negative work, Ft cosine theta. So the gain in stored energy is negative the work done by the force. Gravity did minus 60 joules, and therefore it gained 60 joules of stored energy. So to me, it makes more sense to just derive the potential energy function. But again, this is mostly for people taking the AP. You might have a graph where you have force versus distance, and it will say, you could integrate that to find the work done by the force, which is not constant here. And then the question might say, find the increase in potential energy. So you would be really careful to know whether that was positive or negative force, depending on whether they really meant it to be in the first quadrant. And then you would take the minus sign and say that was the stored energy. Okay, use common sense. If you're working against the force, you're storing energy. But sometimes it is not clear because you just have a graph. You don't have a picture, the story. Okay. I did the example with gravity, so I'm not going to talk about the spring. We'll do this example problem. This is actually, I don't know if this is the first one on the worksheet, so let's just do this. If you want to jump to the worksheet, this is the last slide. A mass moves under the influence of a potential energy given by this random potential energy function. Who knows what's causing it? Bunch of magnets. At the point x equals 1, the force will be, so to find the force, you take negative du dx, so that's going to be negative 6x squared minus 1. So then you just want to know what that is at 1. So don't drop the minus sign. It's going to be minus 6 times 1 squared minus 1 equals minus 6 minus 1 is 5. So it's 5 newtons in the negative direction. You know that they're going to give you the same thing without the minus sign to make sure that you remember that minus sign. The other classic mistakes are to evaluate the original function at 1. So that would be 2 times 1 cubed minus 1 or 1. So that's why this choice is in there. Sometimes people get a little bit confused and they plug in the 1 first, and then they take the derivative of 1, and the derivative of 1 is 0. Okay, so don't do that. You have to derive the function first and then plug in the 1. All right, and I have no idea how they got 7. 8 minus 1 is, anyway, doesn't matter. Hopefully this made sense, and thank you for listening.